Algebra 2 course, Lesson 14, Functions, Part 1. This is Lesson 14 on Functions, Part 1. We'll cover the definition of a function, which includes how to determine if a relation is a function. And we'll look at inverses of functions. In Functions, Part 2, we'll cover operations on functions and compositions of functions. Here's a basic definition of a function that comes from the textbook. And most algebra through pre-calculus textbooks contain a similar definition. A function from a set D to a set R is a rule that assigns to every element in D a unique element in R. And further adding to the definition, the set D of all input values is the domain of a function, and the set of all output values R is the range of a function. We can demonstrate a function by something called a function machine. The funnel at the top is our input, what goes into the function, and the funnel at the right is our output, what comes out of the function. And while conceptually this machine could process anything, we usually process numbers to see what the function machine does to numbers. The first number that we'll try out in our machine is 0. After 0 goes into the function machine, and after being processed by our machine, we find out that we get an output value of 0. Based on our relation from our input to our output, we could have arrived at our answer in many different ways. The number could have been multiplied by 1 or by any other number. The function operation could have been the input value squared, which gives an output value of 0 squared, or 0. The operation could have been the number plus 5, then minus 5, and then many more things as well. Let's try an input value of 1. For an input value of 1, we get an output value of 2. We also place a record of our input and output values in the form of a table at the upper right. For an input value of 2, we get an output value of 4. And for an input of 3, we get an output of 6. The world of algebra often labels the inputs and outputs x's and y's, which we now see at the top of the table, but they could be labeled anything. In function notation, they might have been labeled x and f of x, which is f with x in parentheses. From the information we have so far, it looks like the machine multiplies the input value by 2 to get the output value. The function could be written in algebraic form as y equals 2x. Or the rule can be written in what we call function notation, which is f of x equals 2x. F with x in parentheses is pronounced f of x. It means that f is a function, or depends on what the value of x is. Here's a vending machine that has bottled drinks for sale. The vending machine has 20 buttons total. Each of the 4 buttons on the top row, when pressed, will produce a green and yellow bottle as an output. This relation represents a function because each button will correspond with one and only one type of drink. Let's change this up a little bit. Let's say that someone pressed a button and a green and yellow bottle came out. We know that one of the top 4 buttons was pressed, but which one of them? Since we don't know which button was pressed, we cannot say that which button was pressed is a function of getting a green and yellow drink. So the button being pressed is not a function of the type of drink that is produced from the machine. Let's look at yet another example, a sales tax table. And this is a portion of sales tax table that gives us the amount of sales tax to be charged for any item between 1 cent and $1.15. While some merchants today still use tables like this one to see how much tax to charge, most have the tax calculation embedded in their cash registers or point-of-sale machines. And the embedding is a function rule programmed in the machine to calculate the amount of tax to be charged. Let's say you buy an ice cream cone for 99 cents. Since the cost of the cone is greater than 90 cents but less than or equal to $1.03, the tax amount charged is $0.08 or 8 cents. We can write the sales tax as a mathematical function. The sales tax equals 0.0825 times the price of the item being purchased. We can give different representations of functions. First, a verbal representation. We can say that Manny makes $12 per hour. We can also create what we call an algebraic representation. It might be E equals 12H for earnings equals 12 times the number of hours worked. We can also create a graphical representation, which is really Manny's earnings in a picture form. And finally, there's a numeric representation. A numeric representation is often seen as a table like this one, but could be sets of ordered pairs or even other ways to represent numeric relationships. Here we now have 4 different representations of the same function: verbal, algebraic, graphical, and numeric. And there's great power in the looking at these 4 different ways to express a function. One big part of algebra curricula worldwide is determining what is or what is not a function. Verbally, we say that a relation is a function if each input value has only one possible output value. Algebraically is very similar to verbally, but this time we have an equation. An equation is a function if each input value will produce only one possible output value. We'll now look at some examples of equations that are functions and also some that are not functions. In all these functions, we're using x and y for a coordinate plane. Here are 6 examples of equations that are functions. What do these equations have in common? They each have y by itself on the left side. In order to have a function, you don't need to have y by itself. But to be sure you have a function, you should be able, or hope to be able, to get y by itself. And here's another equation. 4x plus 3y equals 12. Not y by itself, but still a function, because the equation can be solved for y by subtracting 4x from both sides of the equation and dividing both sides of the equation by 3. And there is only one value of y for any input value of x, even though this equation does not start out with y by itself. This brings us to the next point, and that is the next category: equations with x and y that are not functions. First type we'll look at are x equals equations. These equations are x equals -5, x equals 3 squared, and x equals 0. If we graph these equations, it should be obvious that they are not functions because they will be vertical lines. For the first equation, x equals -5, there is only one allowed input value, -5, but for that single input value, y could be any real number on that vertical line. And then we have these equations, which we call conic sections. We'll look at those later in the course. We have a circle, a sideways parabola, an ellipse, and a hyperbola. We'll look at one of these conic sections to see why it is not a function. Let's take the equation x squared plus y squared equals 9 in red at the top right. We'll start solving for y by subtracting x squared from both sides of the equation. Then x squared minus x squared cancel on the left side to equal 0. We bring down what's left and get y squared equals 9 minus x squared. Next, we solve for y by taking the square root of both sides of the equation. So we have the square root of y squared equals the square root of quantity 9 minus x squared. And we're left with y equals plus or minus the square root of quantity 9 minus x squared. And it's this plus or minus sign that makes this equation not a function. We get 2 different output values for the same input value. The plus and minus signs together form a circle mean that this equation is really composed of 2 distinct functions. Here's the y equals plus the square root of quantity 9 minus x squared graphed in the graphing calculators, the top half of the circle in blue. Here's the minus the square root of quantity 9 minus x squared graphed also, and that's the red one at the bottom half. This is why the conic section equations are not functions except for the y equals x squared version of a parabola. Now we're going to look at how to tell if an equation or relation is a function graphically. Here's the graph of a relation on a coordinate plane. To use this method, we need something with a straight edge, like a ruler, a pencil, or a sheet of paper. I even use a finger from time to time. First, we'll use the ruler. We place the ruler vertically on the coordinate plane, and moving the ruler from left to right along the graph, we look for places that the vertical line touches more than once. If the vertical line touches the graph in more than one place, the graph does not represent a function. But in this case, we see that the vertical line of the ruler never touches the graph more than once. We say that this graph passes the vertical line test and is therefore a function. Check. Next, we'll bring back what we looked at earlier when we graphed the equation of a circle. Here, we'll use a pencil. We see that at the far left, the pencil touches the graph once. But here, as we move the pencil to the right, we see that the pencil touches the graph more than once. We say therefore that the equation is not a function. Now we'll try the vertical line test using discrete data, points on a coordinate plane. This time we'll use the sheet of paper. Here's the paper next to the first point, check. Then going left to right, we check the next point. The paper only touches once, here, check. We try the next point, check as well. Then we check the value of x equal to 0 along the y-axis, check. When it's apparent that the relation passes the vertical line test, we declare that this relation is a function because the graph of the relation passes the vertical line test. Now we'll look at numerically testing if a relation is a function. We'll look at tables, ordered pairs, and mappings. First, we'll look at this table to determine if its data represents a function. The critical thing to observe about numerical data is whether or not the same input data gives us different output data. If there are no repeating input values, the data represents a function. There are no repeating x values here in this table, therefore this relation is that of a function. Let's look at this next table. The x values of 1 are repeating. However, since the output values are the same for the same input value 1, those coordinate pairs represent the same point. So this relation also represents a function. Let's look at yet another table. This table also has repeating input values. There are 2 zeros in the input. But in this case, the output values are different. One input of 0 has an output of 5, another input of 0 has an output of 7. Therefore, this relation is not a function. One thing we could do with numeric data is plot the data on a coordinate plane, then use the vertical line test. And here is that data from that last table plotted on a coordinate plane. We see the vertical ruler touching both points here at x equals 0, verifying that this relation is not a function graphically in addition to numerically. Now we'll look at ordered pairs. Here is a set of 5 ordered pairs. Each input value is different. Therefore, this relation is a function. You may notice that each of the output values is the same, the number 5. Having the same output value does not disqualify a relation from being a function. These points plotted on a coordinate plane are data consistent with the horizontal line of the equation y equals 5. Next, let's look at another set of 5 ordered pairs. In this set of 5 ordered pairs, we have 3 repeating 3's as inputs. But because all their outputs are the same for these inputs of 3, this set of points also qualifies as a function. Let's bring the same set down as above, except for that last point. We change that last point to 3, 7. Because for this input of 3 we get a 7, whereas for the other output values for 3 are 6, this set below is not a function. Now we'll look at yet another way of looking at relations. These methods are called mappings and often have ovals like this, or sometimes they're in more irregular shapes and called potato diagrams. Whatever the shape, the concept is the same. This relation is a function because each input value has its own particular output value. Here's yet another mapping. In this example, both the input values of 5 and 9 point to an output value of 6. But this is still a function because we don't have a single input value going to different output values. Let's take these same input and output values and turn them around. The input values become outputs and the output values become inputs. All we did was change the direction of the arrows. In this case, because an input value of 6 could produce either a 5 or a 9, this diagram or mapping is not a function. This is a one-to-many relation. This brings us to an important concept. What may be a function in one direction may not be a function in another direction, in the reverse or inverse direction. And this leads us into the next part of the lesson, inverse functions. We'll start out by looking at a couple real-world examples. Perhaps you remember from earlier in the lesson we looked at this part of the sales tax table along with the formula for calculating sales tax at a rate of 8.25%. The state or taxing entity uses inverse functions to calculate the amount of sales made over a period of time. Let's say that the state receives $153,567 in sales tax revenue over a certain span of time. The state wants to know what were the sales that produced this amount of sales tax. You might remember that the function used to determine sales tax is sales tax equals 0.0825p, where p is the price of the taxable item being sold. In this situation, instead of using the amount of sales as the input value, we need to use the amount of tax as the input value to find the amount of sales. So to do this, we'll bring the formula to the top right and proceed to solve for p. The first thing we'll do is use the symmetric property of equality and rewrite the equation as 0.0825p equals the tax. It's just rotating the equation about the equal sign, which we can do because the sides are equal to each other. Next, we'll solve for p by dividing both sides of the equation by 0.0825. Then 0.0825 over 0.0825 cancel on the left side to equal 1. We end up with the equation p equals 12.12 repeating. That's what the little line segment over the 0.12 represents, repeating digits. 12.12 repeating is the mixed number 12 and 4/33, or the improper fraction 433. These two functions, the one we just determined and the original sales tax function, are inverses of each other. Next, we'll use the formula by plugging in the amount of taxes into our function, and we get p equals 153,567 times 12.12 repeating. And as an answer, we get p equals 1,861,418.182, which represents the amount of sales required to produce $153,567 in taxes. Now we will graph these two functions next to each other on a coordinate plane. And here they are. The blue line is the sales tax function, and the red line is the sales function based on the amount of taxes collected. The units on the coordinate plane are dollars, and each axis is the same scale. One important characteristic about inverse functions is that they are reflections of each other about the line y equals x. The graph of the function y equals x is the black line cutting across the coordinate plane diagonally at a 45-degree angle. A formula that is important in the science of meteorology is the conversion from degrees Fahrenheit to Celsius. There are two major temperature scales used in the world today. Fahrenheit is used in the United States and Canada and is still commonly used and popular in Britain, whereas the Celsius scale is the most popular scale worldwide. If a person in the United States sees a temperature somewhere in the world represented in Celsius, he or she can use this formula to convert degrees Celsius to degrees Fahrenheit. And this is the conversion formula. Degrees Fahrenheit equal 9/5 of the degrees Celsius plus 32. So if I read a weather report for Paris, France, I see that the current temperature is 9 degrees Celsius. With this formula, we will take this value of 9 and plug it into the conversion formula. And here is the 9 entered into the formula. We have degrees Fahrenheit equals 9/5 of 9 plus 32. And that becomes 81/5 plus 32, which decimalizing converts to 16.2 plus 32, and we get 48.2 degrees Fahrenheit. So now, as an American familiar with the Fahrenheit scale, I have a much better idea of what the weather is like in Paris. If we want to convert from Fahrenheit to Celsius, we need the inverse of the Celsius to Fahrenheit conversion. We'll switch the equation around using the symmetric property of equality, and we get 9/5 C plus 32 equals F. We subtract 32 from both sides of the equation. 32 minus 32 cancel to equal 0 on the left side of the equation. Then we bring down 9/5 C equals F minus 32. To cancel out the 9/5 on the left side, we need to multiply both sides of the equation by the reciprocal of 9/5, which is 5/9. 9/5 times 5/9 cancel each other on the left side of the equation to equal 1. And that gives us degrees centigrade equals 5/9 degrees F minus 169, which decimalized is 17.7 repeating. And here are both functions graphed together on the graphing calculator. These functions are inverses of one another, and now added to the graphing is the line f of x equals x in black. Again, as in the example with sales tax, these functions are reflections of each other about the line y equals x. The red and blue lines are reflections of each other about the line y equals x. Now that we've gone over a couple of real-world examples, let's go over the definition of the inverse of a relation or function. The inverse of the relation consisting of all ordered pairs x, y is the set of all ordered pairs y, x. Also, the graph of an inverse function is the reflection of the graph of the relation reflected about the line y equals x. And as we've done so far in this course, in this lesson, we'll go over how to determine inverses of relations algebraically, graphically, and numerically. First, we'll look at numerically. Let's say we have this set of 6 ordered pairs. To find the inverse of this relation, we follow the definition of an inverse relation and switch the values within each ordered pair. The x's become the y's and the y's become the x's. So in finding the inverse of this first coordinate pair, this coordinate -2, 0.25 becomes its inverse ordered pair 0.25, -2. The x coordinate -2 becomes the y coordinate -2 in its inverse relation. The y coordinate 0.25 becomes the x coordinate 0.25 in its inverse relation. The same process is repeated for all 6 coordinate pairs. The coordinate pairs in red are inverses of the original coordinate pairs in blue. We can look at the same process, but this time using points in a table. The table is perhaps the most popular form of numeric representation, and here's the table we're looking at. And here's the table with its inverse relation with all coordinate pairs in red. The x's and the y's have been switched. Now we'll look at graphically. Here we have plotted the points we looked at earlier in our numeric analysis of inverses. Now here's the graph of the continuous function used to determine the input and output values. Now here's the function y equals x plotted on the same coordinate plane in black. The graph of an inverse relation is the graph of the original points reflected about the line y equals x, and here are the inverse points plotted as reflections about the line y equals x. And here's the graph of the continuous function containing these inverse points in red. And finally, we'll look at determining the inverse of a function algebraically. We'll start with this function f of x equals 2x plus 3. The first thing we'll do is convert the function to x and y variables, so we have y equals 2x plus 3. Next, we change the x and y variables, and we get x equals 2y plus 3. Next, we'll switch the function around and put the y variable part on the left side and the x on the right side using the symmetric property of equality. Then we'll subtract 3 from both sides of the equation. 3 minus 3 cancel to equal 0 on the left side of the equation. We bring down what's left, 2y equals x minus 3. Now we divide both sides of the equation by 2. 2 over 2 cancel to equal 1 on the left side of the equation. So this becomes y equals 1/2 x minus 3/2. This function can be written in inverse function notation as the inverse function of f of x, or f negative 1 of x, equals 1/2 x minus 3/2. This looks like f to the negative 1 power, but it's not that at all. This is what we call inverse function notation. These two functions are inverses of each other. And here are the two functions graphed in our graphing calculator in red and in blue. And here's the line y equals x in black. And we can see graphically that these two inverse functions reflect about the black line y equals x. We'll look at another function. It's the same function we saw represented by data earlier in the lesson, and that function is f of x equals 2 to the power of x. We rewrite the function in y's and x's and get y equals 2 to the power of x. Next, we change the places of the x and the y, so we have x equals 2 to the power of y. Next, we use the symmetric property of equality and rewrite the equation as 2 to the power of y equals x. Next, we solve for y by rewriting this function as a logarithmic function. The base of the exponent becomes the base of the logarithm, so we have the log base 2 of x equals y. Logarithmic and exponential functions are things we'll look at later in this course, but I wanted to show a couple types of functions that are inversely related, logarithmic and exponential functions. Next, we'll turn it around to be y equals log base 2 of x. And finally, rewriting an inverse function notation, we get the inverse function of f, written as f negative 1 of x, equals log base 2 of x. And these two functions are inverses of each other. Here are the two functions graphed together compared with the black one, f of x equals x. Note again the reflection of these two functions about the line y equals x. We'll look at another function, g of x equals x squared. The first step in finding the inverse of this function is to rewrite the function with x and y variables. We have y equals x squared. Next we change positions of the x and the y. Next we use the symmetric property of equality and rewrite the equation as y squared equals x. Next we solve for y by taking the square root of both sides of the equation, so we have the square root of y squared equals the square root of x. Then we bring down our result, y equals the square root of x. Now let's graph both these functions. Now let's add the line y equals x. We can see the reflection about the line y equals x. But what happened to the other half of the parabola that now I've drawn in green? The reason that green portion was not graphed as part of the equation is that we need to have y equals plus or minus the square root of x. This is just like earlier in the lesson we solved the equation of a circle. To graph that relation, we need a plus and a minus. Now, here's the graph with the minus square root of x also graphed. And using the vertical line test, we can see that the ruler touches this inverse function twice. This sideways parabola is not really a function because it fails the vertical line test and is therefore not a function. It's in fact two functions. And that's the reason that fails the vertical line test, because it is two functions. And one reason I bring this up is to demonstrate that the inverse of a function is not always a function. We're going to finish this lesson with a couple problems. First problem, the inverse of a function f of x is f negative 1 of x equals 1/3 x minus 2. Which function represents f negative 1 of x? And we are given 4 multiple choice options. If we wanted to, we could take this problem and graph the original function and determine our answer graphically by seeing which one of these 4 multiple choices reflects about the line y equals x. Or we could look at tables and make a numeric representation problem out of it. Stop the lesson and solve the problem, then restart to see if you got it right. The correct answer is C, f of x equals 3x plus 6. To work this problem out, we can start with the equation y equals 1/3 x minus 2. Then we can change out the x and the y positions and we get x equals 1/3 y minus 2. We can swap sides and rewrite the function as 1/3 y minus 2 equals x. We can add 2 to both sides of the equation and we get 1/3 y equals x plus 2. And then we can multiply both sides of the equation by 3 to solve for y, and we get y equals 3x plus 6. And this, of course, is our answer C. Let's look at this last problem. The table below represents f of x. Which table of the answer choices represents f negative 1 of x, the inverse function of f of x? And we have our 4 multiple choice answers A through D. Stop the lesson, solve the problem, then restart to see if you got it right. The correct answer is B. You will see points in table B that are inverse points to the original table for f of x. We could have also graphed the data in the tables and turned it into a graphical representation problem. In this lesson we've covered the definition of a function, specifically how to determine if a relation is a function. We also covered inverses of functions. In lesson 15, Functions Part 2, we'll cover operations on functions and compositions of functions. This has been Algebra 2 course, lesson 14, Functions, Part 1. Thanks for viewing.